In the domain of mobile devices, ambient sensing, human activity recognition, and indoor floor mapping are common targets for attackers who hack devices. This paper presents a novel method, AndroCon, that exploits semi-processed GPS data to sense the ambient, recognize human activity, and map indoor spaces with high accuracy. The study leverages the release of Android 7, which provides precise location permissions, allowing apps to access semi-processed GPS data. The proposed approach uses linear discriminant analysis, unscented Kalman filtering, gradient boosting, and random forest-based learning to yield highly accurate ambient and human activity sensors. The methodology relies on simple machine learning algorithms that can run surreptitiously and provide partially explainable results. The researchers conducted a longitudinal study, collecting semi-processed GPS measurements over a year using different mobile devices spread across a 40,000 square kilometers geographical region. Data was also collected on flights, cruise ships, and high-altitude locations. A thorough characterization of satellite GPS signals was performed, and cross-correlation analysis was used to extract the best set of features that preserve vital information. The results show that AndroCon can easily identify difficult scenarios, such as being inside a metro, a person waving a hand in front of the mobile device, being in front of a staircase, and the presence of people in the room. This is the most comprehensive study on satellite GPS BASED sensing to date. The paper highlights the privacy risks associated with location-based services, which can be exploited to sense the ambient, track human activity, and find more about the layout. The proposed method demonstrates the potential of semi-processed GPS parameters to discern user activity and the ambience in diverse settings, including crowded, open areas, indoor, metro tunnels, and flights. The contributions of this paper include characterizing the potential of semi-processed GPS signals for ambient sensing, showing how apps can covertly capture semi-processed GPS data without consent, and evaluating machine learning models to classify different user activities and ambient settings. Additionally, the paper demonstrates the ability of attackers to infer floor maps, indoor layouts using semi-processed GPS data and user trajectories, without needing access to other ambient information leaking sources. Here is a combined summary of pages 3 and 4 of the research paper. GPS signals contain various parameters, including pseudorange, signal-to-noise ratio, phase shifts, Doppler shifts, and satellite information, which are essential for receivers to correct their data. The GPS processing pipeline at the receiver involves code and carrier tracking loops, which demodulate and identify incoming GPS signals, enabling the calculation of pseudorange, a crucial parameter for distance calculation. By tapping into the pipeline, 9 semi-processed GPS parameters can be extracted, including received signal power, carrier phase shift, multipath interference, signal-to-noise ratio, and Doppler shift. These parameters can be used to extract information about the surroundings, as they are influenced by the environment. In Android, location accuracy permissions, facilitated by Access Coarse Location and Access Fine Location, enable apps to specify the desired precision to access the device's location. Access Fine Location, which requires GPS BASED positioning methods, provides higher precision, typically within 50 meters, and is crucial for mapping or navigation apps. Notably, accessing semi-processed GPS measurements requires Access Fine Location permission. Linear discriminant analysis, LDA, is employed for dimensionality reduction in pattern classification applications. LDA projects the dataset into a lower dimensional space, enhancing class separability through a linear combination of features. This technique addresses the curse of dimensionality and reduces computational costs. The unscented Kalman filter, UKF, is an advanced unsupervised technique used for noise filtering in nonlinear systems. It predicts the future state of a nonlinear system and updates this prediction using incoming noisy measurements. The UKF employs a deterministic sampling approach, accurately capturing the mean and covariance in complex applications. The UKF is widely used in fields such as robotics and navigation, where precise estimation in the presence of noise is crucial. The unscented transform approximates the state distribution using a set of sigma points, which are generated around the mean and passed as inputs to nonlinear functions. The prediction step involves passing the sigma points to the state transition function, and the update step involves passing the sigma points to the observation function. The predicted mean and covariance are computed, and the process noise and measurement noise are represented by covariance matrices Q and R, respectively. The unscented Kalman filter, UKF, is employed to estimate the state and covariance of a system, with equations, 12-14, defining the prediction and update steps. The UKF utilizes sigma points to represent the state and covariance, allowing for the computation of the cross-covariance matrix Quart and residual covariance matrix Street. The Kalman gain KT is then calculated, enabling the update of the state and covariance. The research focuses on the value of semi-processed GPS data, which is available on Android platforms from Android 7 onwards. This data provides access to 9 GPS parameters, including Doppler shift, carrier phase, signal-to-noise ratio, received signal strength, and multipath interference. These parameters are essential for ambient sensing and can be used to infer the state of motion and environmental context of individuals. The Doppler shift, PR, is a significant metric for discerning motion state and environmental context, with high values indicating movement and low values indicating stationary or slow movement. The carrier phase, AdRNG, also facilitates the differentiation between motion states and environmental contexts. The signal-to-noise ratio, CN0, and received signal strength, AGC, are crucial metrics for evaluating GNSS signal quality and distinguishing environmental conditions. The research also examines the correlation among semi-processed parameters, aiming to establish a mapping between M-wave parameters and semi-processed GPS parameters. Real-world data collection was conducted using 5 different Android phones, logging semi-processed GPS data using the Genes Logger Android application. The collected data was supplemented with open-source datasets, including the Kaggle GNSS dataset, to ensure robustness across different phones and environments. The study highlights the importance of noise filtering techniques to ensure the technique works across phones in a robust manner. The collected data was used to simulate diverse user activities and environments, including open grounds, indoors, and different weather conditions. The research aims to mitigate the effects of ionospheric electron density variations and weather conditions on GPS signals, leading to erroneous measurements and potential misclassification. This research paper focuses on utilizing semi-processed GPS parameters to recognize human activities in ambient settings. It begins by discussing the calibration of these parameters with real sensors, specifically examining the correlation between AGC and RSS, which demonstrates a strong linear relationship. The paper then proceeds to detail the feature selection process using linear discriminant analysis, LDA, followed by a description of the machine learning model architecture used for classification. The evaluation setup includes 6 machine learning algorithms: random forest, k-nearest neighbor, support vector machine, decision tree, naive Bayes, and gradient boosting. These models were trained on a dataset collected in various locations such as dormitories, stadiums, markets, and underground metro tunnels, involving 20 volunteers aged between 19 and 28. The dataset was split into 80% for training and 20% for testing, with hyperparameter tuning conducted on a Google Collaboratory Cloud platform equipped with a dual-core Intel Xeon CPU and a NVIDIA Tesla T4 GPU. The results of the evaluation show that when considering individual parameters, AGC has the highest accuracy at 86.7%, while AdRNG performs poorly with an accuracy of 40.6%. However, combining parameters significantly improves accuracy, with random forest and gradient boosting models achieving over 90% accuracy for all settings. SVM and KNN models also perform well, but struggle with the metro environment, which is difficult to classify due to the lack of AdRNG and state parameters. The paper concludes by summarizing the performance metrics for each setting, including accuracy, sensitivity, and specificity. Here is a combined summary of pages 9 and 10 of the research paper. The authors present the results of their ambient classifier models, which achieve high accuracy in identifying different environments such as flight, indoor, metro, open ground, and outdoor crowded spaces. The gradient boosting, GB, and random forest, RF models outperform others, with GB achieving an accuracy of 99.8% and RF achieving an accuracy of 99.5%. The authors also evaluate the importance of each feature in the ambient classification task, finding that AGC has the highest importance score of 0.78. In the context of human activity recognition, HAR, the authors explore the use of Doppler shifts to distinguish between dynamic activities such as walking, running, or traveling in a vehicle. They also classify static activities into 4 classes: sitting, standing, lying down, and hand-waving. The authors use a combination of features, including speed, acceleration, and GPS parameters, to classify these activities. The results of the HAR experiments are presented in a series of confusion matrices, which show the accuracy of each activity for each semi-processed GPS parameter. The authors find that AGC achieves the highest accuracy of 77.2%, while ADRNG performs the worst with a high misclassification rate of 72.6%. The authors also evaluate the performance of different machine learning models using fused parameters, finding that RF, DT, and GB are the best models, achieving a minimum accuracy of 80%. The authors also evaluate the importance of each feature in HAR when they are fused together, finding that AGC has the highest importance score of 0.88. This further supports the claim that using fused parameters improves the accuracy of HAR. The results are presented in a series of figures and tables, including Figure 7, which shows the ambient classification confusion matrix for different models, and Figure 9, which shows the feature importance test for ambient classification using the GB model. The performance of various machine learning models for activity classification is evaluated using a dataset with semi-processed GPS parameters. The results are presented in Table V, which shows the accuracy, sensitivity, specificity, and FS score for each classifier. The random forest, RF, model achieves the highest accuracy for hand-waving, 77.5%, lying down, 97.2%, sitting, 91.2%, and standing, 82.7%. The decision tree, DT, model also performs well, with accuracies of 80.7%, 84.9%, 85.1%, and 87.9% for the respective activities. The gradient boosting, GB, model achieves accuracies of 82.4%, 96.9%, 86.7%, and 82.8% for the respective activities, outperforming the K-nearest neighbors, KNN, and naive Bayes, NB, models. The support vector machine, SVM, model performs poorly, with accuracies of 60.3%, 93.4%, 38.3%, and 44.8% for the respective activities. The robustness of the method is assessed by conducting experiments with varying environmental conditions, satellite vehicle ID, SVID, density, and test, train split. The results show that the method is robust to changes in these parameters, with the accuracy remaining above 91.5% for ambient recognition and 83% for activity classification. The feature importance test for human activity recognition is presented in Figure 12, which shows the importance of each feature in predicting the activity. The results indicate that the acceleration, AGC, and state features are the most important for predicting the activity. The confusion matrices for each classifier are presented in Figure 11, which shows the true positive and false positive rates for each activity. The results indicate that the RF and GB models have the highest true positive rates and lowest false positive rates for the respective activities. The results of the experiments with unseen events are presented in Figure 15, which shows the accuracy of the models on a new dataset collected at different locations. The results indicate that the GB model has the highest accuracy for ambient recognition, while the RF model has the highest accuracy for activity classification. The research focuses on utilizing semi-processed GPS data to create an indoor floor map, overcoming the limitations of GPS signals in indoor environments. The authors investigate the variability in accuracy across different phones and environmental conditions, observing a significant difference in accuracy between phone models and times of day. They employ a UKF and LDA approach to mitigate noisy readings and handle varying ambient conditions. To create the indoor floor map, the authors studied GPS RSS patterns in a large indoor area, utilizing a commercial tool to generate a heat map depicting relative GPS RSS levels. They introduced 2 access points outside the site to simulate a GPS setting and observe a high correlation between the scaled data and real-world GPS signal intensity. The authors propose a trajectory creation methodology, relying on multiple users to collect semi-processed GPS parameters, human activity recognition, HAR, fingerprints, and trajectory information. They employ a trajectory alignment algorithm to merge the results and identify landmarks, such as pathways, stairs, elevators, rooms, and obstructions. The algorithm involves using a transformation matrix to adjust curvilinear paths, translation, and rotation. The authors evaluate the accuracy of classifying activity landmark points, collecting data from 10 volunteers and using graph optimization techniques to refine the locations of the ALC and NALC trajectory points. The results show that the generated map closely matches the real map, with a maximum error of 4.10 meters for the graph discrepancy metric and 3.41 meters for the shape discrepancy metric. The authors also assess the landmark detection accuracy using a GPS BASED HAR system, achieving an average accuracy of 90.15% with a random forest classifier. Finally, the authors discuss the privacy risks associated with exploiting semi-processed GPS data and highlight the importance of Android's enhanced privacy options, such as selecting between fine and coarse location permissions, to restrict app access to location data. The proposed approach, AndroCon, utilizes semi-processed GPS signal parameters to recognize human activity, sense ambient conditions, and construct indoor floor maps. This method does not rely on GPS coordinates, Wi-Fi signals, or camera data, making it a unique solution that addresses the limitations of existing approaches. The authors conducted an extensive set of experiments, collecting data from tens of volunteers, various phones, and diverse scenarios, resulting in a robust dataset. The results show that AndroCon can achieve high accuracy in recognizing human activity and ambient conditions, with a range of 99.5% in controlled conditions to 87% in uncontrolled conditions. The approach also demonstrates the ability to construct indoor floor maps with a maximum error margin of 4.1 meters compared to the ground truth. Additionally, it can classify points of interest within an indoor layout, such as elevators, stairs, and rooms, with an accuracy of approximately 90.15%. The authors highlight the vulnerability of existing Android systems, which do not address the use of semi-processed GPS data, leaving approximately 90% of users exposed. This vulnerability can be exploited to compromise user privacy, emphasizing the need for responsible disclosure and mitigation strategies. The related work section provides a comprehensive comparison of existing approaches, including image-based solutions, Wi-Fi-based solutions, and GPS BASED solutions. The authors note that image-based solutions, while accurate, raise significant privacy concerns, while Wi-Fi-based solutions rely on the availability of good quality Wi-Fi signals. In contrast, GPS BASED solutions, such as AndroCon, offer a covert and reliable approach. The authors also discuss the limitations of existing approaches, including the reliance on visual cues, high costs, and intrusive methods. In contrast, AndroCon offers a non-intrusive and cost-effective solution that leverages semi-processed GPS data. The approach draws inspiration from existing methods, such as Zhou et al.'s graph optimization method, but improves upon them by utilizing semi-processed GPS data and eliminating the need for Wi-Fi access points. This section of the research paper presents a comprehensive overview of various indoor floor mapping approaches, comparing their methods and techniques. The authors provide a detailed table summarizing the approaches, highlighting the use of different sensors, such as IMU, GPS, Wi-Fi, and lidar. The table also showcases the diversity of methods employed, including user trajectory alignment, link node approaches, and fusion of multiple sensors. The paper then delves into an extensive literature review, covering topics such as location-based services, human activity recognition, and dimensionality reduction. The authors discuss various machine learning algorithms, including support vector machines, random forests, and neural networks, which are used for activity recognition and classification. The review also touches upon the importance of data scaling methods, data fusion, and sensor selection for improving the accuracy of human activity recognition. Moreover, the authors discuss the challenges and limitations of existing approaches, including issues related to GPS signal strength, multipath effects, and ionospheric delays. In addition, the paper explores the role of crowdsourcing in indoor mapping, highlighting its potential in constructing and refining indoor maps. The authors discuss various techniques for integrating multiple sources of data, including GPS, Wi-Fi, and inertial measurements, to achieve more accurate and robust indoor mapping. The review concludes by emphasizing the need for further research in indoor floor mapping, particularly in addressing the challenges of scalability, robustness, and generalizability. The authors highlight the importance of developing more sophisticated algorithms and techniques that can effectively handle the complexities of real-world indoor environments.